Hi everybody, this is an introduction to the bioserver software applications which will be used during the Drugathon. First things first, let me introduce you to Caesar. Caesar is bioserver visual drug discovery dashboard. By clicking in the upper left corner, we have a drop-down menu popping down and can load our target structure which you can access through the Drugathon website. We select the Drugathon structure and open it. And now Caesar will calculate some important values like the protonation states of residues and the ligand, the binding affinity of the ligand, clash properties, and so on. Once the calculations are finished, we can now see our dimer popping up in the window. By clicking on the right mouse key, we can twist and turn the structure around. By using the wheel, we can zoom in on the structure and also zoom out. By using the control key on our keyboard, we can also move the structure with the right mouse click around. On the left side, we can see two ligands popping up. If we now click on the structure, a 2D structure will appear in the window below. Same goes also for the second structure. We'll now go with a structure with a higher binding affinity and confirm this ligand as our main target of interest by clicking on this blue circle here. If we now click on the Apply button, Caesar will define the residues around the ligand as part of the binding site. If we now click on the ligand once again and use the space key to zoom in, we will see that Caesar has loaded our target structure. It has defined the residues around the ligand and also added the water molecules around it as part of the binding site. Next, I would like to introduce you to the different options of customization within Caesar. By clicking on the Palettes menu, you can select the background color of your choice. I will now select black to make the colors pop. Further, you can also define the layout of Caesar by clicking on the different layout options. In the theme, you have the options to go with a dark theme, which I use right now, or if you prefer it a little bit more lighter, you can also select the light mode. For colorblind people, there's an option to decide which colors you would like to use, which indicate good or bad interactions. Right now, I have the green-red one, but there's also the option to select the blue-red one. In the visualization menu, you can select which features shall be displayed in the graphical interface. Height coloring indicates those spheres around the individual atoms, which is also correlating to the contribution to the overall binding affinity. You can select to display or hide hydrogen bonds. You can also select the torsion coloring, which I mention later on, and also molecular clashes, unoccupied spaces, and what's the most important likely, the binding site surface. You can also select which color scheme you want to use for the binding site surface, like element coloring or lipophilicity coloring, and you can also select if you want to have the surface in transparent or in opaque. I will go with transparent. Now I want to introduce you to some important features of Caesar. If you have zoomed out too much, like in this case, and you cannot find back, or this whole structure went missing, you can always use the space bar on your keyboard to zoom back in on your ligand. Now let's talk about the labeling option of Caesar. By pressing L on your keyboard, we see now a tag popping up close to our cursor, or if you go to the Label and Measure menu, we can also select the Show Label feature and now start labeling atoms, groups, residues, whatever you want. Let's take a look at this sulfur atom here. If we now label this sulfur atom, we receive some important informations. This is a height value. The height value is a calculated value which represents the contribution of this particular atom to the binding affinity of the ligand. In this case, we have a negative 3.8 kJ per mole, which means that this sulfur atom increases the binding affinity of the ligand. If we now compare it to this nitrogen here, which is red, we can see that this nitrogen does not contribute well to the binding affinity because of this positive value of 2.9 kJ per mole. In the Drugathon, we aim to design novel drugs, which means that we want to create compounds that have only green spheres around the atoms, which means that every atom is happy in the binding site and therefore increases the binding affinity of the ligand. We can also ask Caesar to display the interactions that result in the height value here. Same goes also for the other one. What height does is, height stands for hydrogen bond and desolvation energy. So basically, solvation-desolvation, which is also presented here. Desolvation means that if a lipophilic atom, like the sulfur here, becomes buried in a lipophilic binding site, it is more happy because it's not exposed to a hydrophilic environment. In this case, it's surrounded by lipophilic residues, like here and here, which therefore also increases the binding affinity. Sometimes the interactions with the residues in the binding site, like hydrogen bonds, also can contribute to the binding affinity of the ligand. The spheres, in this case, have two purposes. One is the size, which reflects how well or how much contribution of the height value to the overall binding affinity is, and also the coloring. Green, or if you have the colorblind mode on, blue. Green and blue means good contribution, and red means bad contribution. So basically, what we want to do, we want to predict new ligands, and once we have docked them or have found a pose for them, and they do not display any red coronas, then we have reached our goal, because we will likely have a very good ligand with a very high binding affinity. Further, as I mentioned, it is also possible to color the torsions. Now maybe take a look at the ligand, and you see that the bonds between atoms receive a color code. In this case, if we now label those torsions, we can see a distribution histogram. High bars that are closer to 1, means that these are empirically measured values, and if our torsions are within those good representative values, then it is also very likely that this bond angle is also present in nature. If we now compare it to maybe a red one, it becomes more apparent. So this is a torsion that is not seen very often, so it's unlikely that it's just an intermediate state. If you design ligands, please keep in mind that we want to design ligands which have only green or at least only few orange colored bonds. Further, we can also display molecular clashes. In this case, they are non-present. And what else? So since we can also label residues, we can always ask Caesar, hey, what is this residue? And you can see this is isoleucine 150. Same goes also for the waters around in the binding site. Next, I want to introduce you to the binding site mode. If we hover over the central key element, up here, the icon, we can switch modes within Caesar. This is our gateway to go to the binding site mode. Now we click on the binding site mode, the green pocket. And within the binding site mode, we can interact with different structure elements of the target. If you click on the show and hide unoccupied pockets icon, Caesar will start calculating and searching for potential binding sites within the target. Let's give it some seconds. What we can see now, that we have many different cotton candy clouds popping up with different colors. And on the left side, we have a new table popping up with different values. So if we now take a look, maybe if we now hide the binding site surface, you will see that here we have our original binding site, a light bluish color, which is pocket number 4 with 30 residues. We get the dock site score, which is an indicator of how druggable a binding site is, and we get other informations like the number of hydrogen donors and acceptors, the hydrophobicity of the binding site, and also the surface and the volume. So here we could actually check if there are several binding sites for the target in question. Obviously, we have the binding site of our thiamine diphosphate here, which is the bluish one, which is also our defined binding site. And if we now scroll around a little bit, you can see that we also have a binding site here. The question is if we want to address this one, because it's actually a binding site built by the dimer per se, which is not the case in reality, so maybe it's not a perfect target. But the pink one is also part of the dimer, so I wouldn't go with this one. But here we have a very small binding site, which is only the green one, this one, and also the purple one. So in theory, we would still have other binding sites which we could use to target the drug with drug candidates. If we now click on the binding site, we can see that residues are selected. They are now part of the binding site, but we don't want to do that. We will simply work with the initial binding site. So basically, with the reset button, you can deselect every residue, and once you click on something, you can add those residues to the binding site. It is also possible to use the drop-down menu below, which we can see the sequence of the target. We can even search for particular residues we want to include, like proline. Now we see all those prolines popping up, and we can click through them. And if we want to add a particular residue to our binding site, we can click on the residue and add it to the binding site. I will now once again confirm my initial binding site as a selection. I have removed the proline from the search bar to not irritate you. And for my next molecule, I want to go back to the proteins mode. An important aspect of CSER is that it always works with one binding site and also with just one ligand. So if you want to do something with a ligand, you always have to take your ligand by right-clicking it and transfer it to different modes depending on what you want to do with the ligand. Now I want to show you the molecule editor mode, and therefore will select my ligand and transfer it to the molecule editor mode. In the molecule editor mode, you can modify and customize your ligand. I will now zoom in on my ligand with the spacebar. And as far as I can recall, this particular nitrogen here was very unhappy. So maybe I will just select this one and change it for a carbon atom. I can do it by clicking on C as a shortcut on my keyboard, which will now modify this one to a carbon atom, or as another option, I can select this one, go to the change element icon, and select carbon. Once I'm finished, I have to export my newly designed compound by clicking on this icon here. And you can see we have a huge shift, a huge gain in affinity for this ligand, because this predicted estimated affinity by height has moved to the left. Please be aware that this scale is logarithmically scaled. So basically, this nanomolar and micromolar, this is a difference of 1000. And if we now click on our newly designed ligand, we can see that this carbon atom became very, very happy, and due to a little shift, we can also see now the hydrogen bonds, which we can toggle on and off, and you can see how it now can really beautifully interact with the backbone of the target structure. If we want to further play with this compound, we can just press on the play button and then add new elements to our structure. Maybe we want to add something in this part. I want now to add a ring, like a cyclopropane, by right-clicking on the atom, add ring, cyclopropane, and there we go. We added a 3-membered ring in this position where the methyl group was. And if we now export it, we can see if this modification contributed to the affinity or if it decreased the affinity in this case. And as far as we can see, it did not increase the affinity too much, so almost no gain, even maybe a slight loss in activity. In the molecule editor mode, there is also possible to create completely novel molecules, starting with an atom, like let's maybe start with a chlorine. We don't see it yet, so if we now click on our space key, we can see that it's placed here. We can also create whole new ring systems with this one. Let's start with a benzene or a phenyl ring if it's substituted, and so on and so forth. You can also play with the structure, so you can right click on this one, add a ring structure. Now I will just go with this part. Again, I can add an atom maybe, like a double bonded oxygen in this case, and also by playing with the numbers, either here by clicking on the bond type, you can select which bond type you prefer, like single bond or double bond, but you can also use just the numbers on your keyboard, like 1 and 2 and 3, although this is a very dumb idea. So let's just go with 2. And as always, once we are finished, we can export this one. And obviously, since it's not part of the binding site, I'll zoom in a bit. You see how far away it is. It has obviously no binding affinity, or no calculated binding affinity in this case. You can also change the charge type of your compounds, the element, and also, in case of stereochemistry, also play around with this particular button. Next, let's go to the Inspirator mode. For this, I will now select my initial ligand. Let's zoom back in with a spacebar. Right-click and add it to the Inspirator. The Inspirator mode is our, I would say, ideation factory. So every time we need some inspiration to design something, this is the place to work, our yellow Inspirator mode. The Inspirator mode offers us several options and tools to create new compounds and to create some new ideas. If we now click on a bond, we can see that one part of the ligand is blurred out. And if we do it the other way around, now this part is blurred out, so we can change the direction of the side we want to work on. So right now I want to create some new ideas for this part of the ligand, this heterocycle. And if you now pay attention to the left part here, you can see that the growing function is popping up. This is the novel FastGrow algorithm. It searches for complementary molecule fragments that complement the shape of the binding site here. So we want to find something that perfectly fills out the space in this area. If you now click on the growing functionality, Caesar will start looking for perfect replacements, shape-based, geometry-based, for this particular area. Per default, a library of 12,000 compounds of 12,000 fragments is included in the standard version, but we also have a more chemically diverse library available free of charge, obviously, on our website, consisting of 120,000 fragments and compounds. And as you can see, within seconds, I use the larger library. 120,000 fragments have been screened, and now I have them as part of my library and can screen through them to see if any of those compounds fulfills the needs in this binding site. Since they don't have an affinity yet, I obviously want to also calculate something here. I will now check all of them by clicking on this icon here, check all, and now I want to calculate the binding affinity, so I will click on the calculator and the estimated affinity selection and wait for Caesar to calculate some values for height. What we can see here is that compared to our initial compound, we have now 3 novel candidates with improved binding affinity. And we can see how they even interact in the binding site, forming hydrogen bonds, which is always a good idea. Here we have a very interesting substitution. Now it's questionable if this protonation state is a good one. And also, this one looks also very interesting. So, 3 novel ideas within a few seconds. If you want to have more results, we can go to the parameter settings of the Inspirator mode and also increase the numbers of solutions which shall be calculated by Caesar. Further, it is also possible to define pharmacophore constraints. So if we want now to have maybe, I don't know, an aromatic system here, in this part, we can now just move our pharmacophore constraint sphere to this area, or select 2 of those atoms and set the center of the sphere between those 2. We can play around with the size and also select a variety of parameters or parameter of pharmacophore features like an aromatic residue, carbon atoms, aliphatic, ring systems, and so on. In this case, I want to look for something aromatic in here in this area to make it more similar to my initial structure. What's also possible, just as an idea, if I want to have something that is a perfect hydrogen bond partner for this residue part here, you can see if I click on it, a purple sphere will appear, purple circle, and now if I ask for possible interactions, I can now see 2 areas for hydrogen bond donors. If I select maybe this one here, let's go with this one, I will set my sphere to this area and will ask for an hydrogen bond donor in this area. So please, now let's take another search with FastGrow. And once the calculations are finished, we can now screen again through our results, and we can see that Caesar has found some interesting examples here to complement our requested concept of a hydrogen bond donor in this position. So this is how FastGrow works, and you can do it for everything. So if you want to search maybe for something to replace a diphosphate here, you can also use FastGrow to screen for something to replace this particular structure, because it's not very interesting for, it's not a good feature for a drug itself because of the many negative charges here. Okay, now I will just uncheck everything, check all, and just select this one, because I want to remove all those structures from the Inspirator mode before I show you the next feature. So now just delete those molecules, et voila. Next, I would like to introduce you to the ReCore functionality. For this, I will now switch this one off and also remove the pharmacophore constraint which we placed there by right-click, delete selected constraint. Now I will select within the 2D window, like here, or in the 3D window, the areas of the compound that I want to replace. Those purple borders are defined now which part of the molecule shall be kept and which part of the compound shall be replaced. In this case, I will now replace the middle heterocycle here with something else. If I go to the system settings and to the Inspirator mode, I can now select which ReCore index I want to use. We have 4 available, and for now I will go with the PDB ReCore index. So the PDB ReCore index is actually based on PDB, empirical PDB data that was published, and the compounds within from all PDB structures were collected and fragmented. So now we have 3D coordinates of those structures, which we can use to replace parts of our molecule. I'll now just quickly go back. And now I want to use I want to receive 10 solutions for a replacement of this core. It would be also possible to define pharmacophore constraints even in this case. But for now, I will just let it roam freely by clicking on the now active ReCore button. And one click. And I got 10 solutions. If I want more, I can just click on the Give Me More Solutions button, and we'll receive 20 solutions in total, and so on and so forth. And now, if I click through the solutions that ReCore generated, I get some ideas how to replace this particular scaffold. Now it becomes a bit more interesting, the guanidine ring. And if I would now calculate affinity parameters, I may also receive some new ideas how to replace this particular part of the ligand for something that is maybe more active. So I now calculated the affinities for the compounds from ReCore, and we can see that we got a selection, some drifts here and there, and if we now rank them according to their estimated affinity, we can see that we get some interesting results here and there. So obviously this one also forms an additional hydrogen bond and may stabilize this phosphate chain in this particular area through an additional hydrogen bond interaction, which is very interesting, and so on and so forth. If you want to compare your structure with the initial structure, it's also possible to tag the 3D structure of your compound and even colorize it for easy comparison. Just tap it here, tag it, color it, and then you can compare your structures. It's also very important to mention that ReCore is a pure geometrical replacement. So it's always important to additionally validate the proposed structures either by docking or additional other methods. Now I want to show you how to search in vast chemical spaces with infiniSee. For this, I will select now randomly one of the compounds that I generated with ReCore to see if I can find something that is commercially available in one of our partners' chemical spaces. I will now just copy this particular structure because I really like this hydroxy group here. By right-clicking into the 2D window, I can ask Caesar to copy it to a clipboard as an SD file. This is infiniSee. infiniSee is our chemical space navigation platform. It can screen billion-sized compound libraries to search for similar compounds. Now it has a similar system as Caesar. If you like it dark, you can go with the dark mode. If you want it a little bit more happy, you can use the light mode. And for consistency reasons, I will just pick the dark mode. Now I will load our structure from Caesar. Because I copied it to my clipboard, I can now just copy paste it. Or another possibility would be to drag it from one window to another. Now I will just copy paste it here, and voila, this is our query compound. It's also possible to draw your own compounds to search for something new, or use the easy sketch to modify your compound. Like in this case, I want to remove the second phosphate because it's just a really labile structure that is easily metabolized, but I will keep this phosphate group to see if infiniSee can find something that is more or less related to a phosphate group in this position. Once I've finished, I will just export my compound, and here you can see that only one phosphate group is present. By adjusting the search parameters, I can select how many results I can receive from infiniSee. I can go up to 100,000, which is maybe a little bit too much for this scenario. I will stay with 100 results. Here I can select how similar those structures are supposed to be to the query compound. One is please search for something that is completely the same structure, exactly the same structure, and if I decrease up to 0.8, I will get structures that are just a little bit more fuzzy, pharmacophorically related to this one. Here I can adjust what the minimum similarity of compounds will be. 0.8 is a very rational choice here. If I want to have exact this structure, I can increase it up to 1, or I can go to 0.0, where every compound will be displayed more or less. I will keep it at 0.8 as a standard default setting. And what's really interesting here is the total diversity. So if I lower the total diversity, the results that will pop up on the right will be more diverse, while if I increase it to 1.0, all those compounds will also be related to each other at some point. Now I have my settings selected. What's next is to decide which library I want to use. In this case, we have 3 libraries that are important to us. The first one is the Galaxy space from Wuxi Lab Network. The second one is the real space from Anamine, and the third one is ChemWire from Ottawa Chemicals. All those vendors can be found here, and we decided to go for those 3, namely Galaxy, ChemWire, and real space. So those 3, because those are our partners' chemical spaces, where they can produce those compounds that we find in a make-on-demand manner, so everything that we will find with infiniSee will be also commercially available for us. So I will now, just for demonstration reasons, go with just the Galaxy space. I have my settings selected already, and what's also possible, if you want to highlight particular structures, you can also click on them and then adjust how important they are for your search. So if you want to have this structure present in your result compounds, you can increase the similarity for this one up to 1.0, which means it shall be included, obviously. If you don't want a particular structure, you can just decrease the similarity for this one by going down to 0.8. But for now, let's do not limit ourselves and just simply start the search. And what infiniSee does, it now searches within those combinatorial spaces for compounds that are similar to our Cree compound. The underlying algorithm behind this one is called F-trees. And what F-trees does is F-trees looks for compounds that are related to your structure. And you see those were 12 billion compounds of the galaxy space, 12 billion screened within seconds. And if we now click on just the first one, we can see how they are related. This is also a very important aspect of infiniSee, as it tells you why it thinks that those compounds are related. And you can see through the color coding easily which areas of the compound are more or less similar. If you now scan through those results, we may get some good ideas of how to replace this one. So, as I told you, infiniSee finds also, let's say, bioisosteric groups, in this case isofronate, that substitutes this phosphate group here. If you go lower, we will find maybe something else. Let's see here, sulfonamide, which is a really good substitution, and so on and so forth. What's important though is we have those compounds and we have also similarity score, and the similarity score is a little bit lower than 0.9, so we should always validate our results. Since we have a structure available, it is always a good idea to take those structures that that infiniSee provides you and use them for additional enrichment by docking to see if those compounds may really bind in the area you're investigating. So now just select this one, maybe this one, maybe this one, and I will also use this sulfonamide, or I can even select all of them by clicking here and then check all, but I just now go with those 5 compounds, and by clicking on this save icon, this disk icon, I can copy them to my clipboard as smiles to transfer them to Caesar. Now I want to introduce you to the docking mode. By going to our menu button, I will now select the red one, the docking mode, click on it, and enter the most core functionality of Caesar. As you may recall, we have copied our interesting compounds from infiniSee as smiles and can now copy-paste them here into this window or just drag and drop them, and voila, here are the compounds. And the question is, how do these compounds bind in our binding site? For next, I will go to the parameter settings. I will go with, let's go with just 5 poses that will be generated. I can also play around with the clash tolerance, so if we would have a very tight binding site, it could make sense to kind of like allow a little bit more freedom here by setting the standards too high, to allow a little bit more of unconventional conformers maybe of the conformations for the ligands. And we can also adjust possible conformations of 6-membered rings. For now, I will just go with the one with the lowest energy, which will be the chair conformation. It is also possible to define pharmacophore constraints, as previously in the Inspirator mode. The docking mode has 3 different docking methods, as I would say. One is the standard docking, so this is just the usual placement of a ligand in the binding site. The second one is a template docking, where you can define a template by clicking here on a structure, and it will be set as a template molecule, so all compounds will be docked accordingly to this structure. And we also have covalent docking, which requires a little bit more explanation, but we have a guide available on our website as well in the Caesar help section. So I will now start my standard docking by clicking on it and just wait a few seconds for Caesar to generate some poses. The calculations have finished, which didn't take too long. And now we have some poses. I will just click through them so we can see if there's anything that might be interesting. So a little bit unusual, but very nice interactions in the binding side with the hinge binding region. Yeah, this is even better. We can also now rank those compounds. Yeah, it seems like this is a very good idea for a substitution at this point. So basically, this is how you use the docking mode. We now have a better idea of how the compounds bind, and this will be a new point for further designing. So since we have now a new motive, we could just use the going functionality in the Inspirator mode to see if we can elongate this compound and make it bigger by maybe going into this direction. If you want to submit your compound, you just can select the compounds you want to share with us and then go to the export checked molecules to file, and then please save it as an SD file and send it to us through the submission page. What I would suggest to you, just as an idea, it's always a good option to select the compounds that you had in mind, like those both. You see an interesting binding motif here, and just park them into the analyzer mode. Here, clicking on Add Molecules to Mode and then to the Analyzer mode. This one can be used to filter your compounds to see if there's any way to prove them. Some additional remarks on my side. It's also possible to calculate physicochemical properties, admin properties for those compounds through our Optibium extension. And now, with the Optibium extension, we can calculate also important values like paraglycoprotein category, brain permeability, brain blood barrier permeability, and so on and so forth, which will maybe be also interesting for some compounds or for the best candidates. Yeah, that's basically the introduction. So now it's completely up to you how you want to proceed from this point. Be creative. Yeah, the only important factor is if you want to submit your compounds, please submit them as an SD file to us. And don't pay too much attention on the estimated affinity. So you don't need any particular values. We will calculate for them from your results. You can also calculate them yourself by saving them as an Excel sheet. Or look into the SD file that you generated. There are also numerical values available for the upper and lower boundaries of the binding affinity estimation. So use this just as the indicator. So once you've reached this region where you have nanomolar affinity predicted, these are good compounds, and these are the compounds that you also want to have, because you want to have a diverse chemical set of compounds to purchase several of those to increase the hit rate. And please also pay attention that the compounds that you suggest are also commercially available. So since you will likely use infiniSee, infiniSee guarantees that the compounds that you find are also commercially available, at least if you search in one of the three partner spaces, Galaxy, ChemWire, and RealSpace. You are also free to use enumerated libraries from, I don't know, Live Chemicals or the Real database. It's completely up to you. Just be creative. Do whatever you want. Feel free, be creative. And the most important point is actually that you also enjoy this event, and yeah, maybe you will also learn a thing or two with our software applications. So thank you for tuning in. We will see you in Gathertown, and have fun. Goodbye.